All right, so today, mining big data, what are we doing? We're doing similarity. Yay! When two things are the same. What are we trying to say here? Wait, is this the right one? Yeah, this is the right one. Okay, so today what we're going to be doing is reviewing Jacquard's and cosine similarity, which should have been in the online learning. We're going to have a look at min hashing, and we're also going to be looking at local sensitivity hashing. So that's basically what we're doing. But let's talk about it. What are we trying to do? We're trying to say these two things are the same. The problem, I think, like that's pretty easy to do in computer science to say, are these two things the same? Because what you do is you say, is A equal to B, right? If they're the same. All right. So what if they are similar, right? Like we have a definition of, like similarity. I have something that is like 80% similar to something else. That's kind of okay if like the way in which it is similar is all very, very constrained. So for example, I might be able to say two people are similar if they have a similar height and a similar weight, but maybe their name can be different and I don't care, and things like that. But the thing is, when we're talking about similarity now, what we're really talking about is groups of things, right? Where I have a group and the group is kind of unordered. And I think that is the main thing to understand here is that like, these two groups are the same, even though they're not in the same order. So normally if I were to try and compare if these two things were identical, it would be, I couldn't just say is the first thing the same as the other first thing, is the second thing the same as the other second thing, because these things could be in different orders. Now I need to compare every element to every other element and see if there is a correspondence between the two so that I can group them into pairs and then mark off each of the pairs. And you can imagine that if your groups contain a lot of elements, that's a big, expensive process, right? So, and if we want to work out how similar two groups are, like if trying to, work out, let's say that each group contains, 10,000 elements, and we want to say, are these two groups the same? Now I need to, do a 10,000 by 10,000 algorithm to compare each element to each other element to see if, each element in group one is the same as each element in group two. And now I've got two groups, so I've got to do it twice. And if I've got like 10,000 groups, then I've got to do it 10,000 times. And you can see how this really quickly balloons into like lots and lots and lots and lots of data, lots of comparisons, and we get kind of grumpy. And the question is, how correct are we? How, like, even if we've managed to make this idea of similarity or dissimilarity, like, did we get the numbers that we wanted? This one's a cute little one down the bottom. One of my favorite, what do you call it? I don't know, silly maths questions. One of these things is not like the other. Does anyone have an answer to this question? Which one do you think is the odd one out of these 5 objects at the bottom? Like 1, 2, 3, 4, or 5. So one is the red square with the black border. One is the red square. One is the red circle with a black border. One is the green square with a black border, and the other one is the little square with a black border. Does anyone have a guess? Which of these is the odd one out? 1 and 5. Oh, well, that's interesting. 1 and 5. That is an interesting guess. Most people say 3, right? And the reason they say 3 is because a circle, it sounds like a different thing to a square, I think is the main reason they say 3. But the answer is actually, as Shuyu has said, oh, Daniel says 2. Shuyu said 1 and 5. The answer is actually 1, believe it or not. And the reason the answer is 1 is because it is the most the same to all the others, right? That is to say, to get from 1 to 2 is 1 step. To get from 1 to 3 is 1 step. To get from 1 to 4 is 1 step. And to get to from 1 to 5 is 1 step. Whereas to get from like 3 to 4, you have to go via 1 to 4. Yeah. So this is like a nexus point, and that's why it's the odd one out, because the other ones are further away from each other. It is the most similar. The most similar object is the odd one out because it is the most similar. All right. That's pretty silly. That's an aside. Okay. So why do we care? Like, like, just at a fundamental level, why are we even bothering to do this analysis? And the logic is, if two things are already largely similar in one sense, they may be similar in another sense. So if I can get two things and I can say these two things are similar, right? I might then be able to use that information to say, oh, because they have these qualities and they are similar, they're part of the same sort of broad cluster of things. They have like 90% similarity. I might be able to make predictions about both of them, that they both act the same way. I also might be able to just go, one is a plagiarism of the other one, right? Like, as in someone took this and they just copy and pasted it. So I can go, oh, is this original data or is it not? The other option is, like if for redundancy, if I have two things and they're basically the same, why would I bother maintaining both? Maybe I can just, avoid duplication. Yeah. So the plagiarism example is, these two essays, have identical words. So this is the observation, right? And so my prediction would be that they have the same author, right? Like, that's what plagiarism is at its core. We're not just detecting plagiarism. What we're doing is we're saying, based on the similarity of these documents, I'm going to assume that the person who wrote the documents is the same, right? That's what plagiarism actually means, right? So for big data, it's a thing because you can imagine like this is the similarity of a big ON comparison. I have large numbers of groups, right? And I have to compare every group to every other group, right? And inside every group, I also have to when I'm comparing one group to another group, I'm also doing an ON squared kind of thing where I'm going each element of each group. So like each of these boxes is actually like another similarity problem. So we're doing big similarity problem of small similarity problems. So that's not good, right? We also have this idea of identical versus similar, right? Like, so if I have 1,000 documents, and I've already said this, containing 1,000 characters, to compare the two documents are identical, I must compare all 1,000 characters in both. Yeah, fine. All right. So, this is not too hard to do. All I have to do is I compare red to red, orange to orange, yellow to yellow, green to green, green to green, right? Super easy. If I have 1,000 documents and each document contains 1,000 characters, and now to compare two documents that are similar, I must compare everything to everything within the document, right? So instead of just comparing like 1,000 comparisons and then doing the comparison of 1,000 documents, right? What I'm doing is I'm still doing 1,000 documents, but now I have to compare everything to everything here, right? So like these two are similar, right? In fact, they're exactly the same in a sense because both of them contain the same colors. But in order to work that out, I'd have to compare the red to the first, one with one, one with two, one with three, one with four, one with five, right? And we can see here, while I don't think there's a huge amount that we can do about this similarity on the right, because if we really wanted to say all of our documents are the same or they're all different, we kind of have to include all of the documents in our calculations, right? Like I can't just pretend a document I've never read is similar to another document I've never read. I have to have read both and compare them at some level, right? But I can at least get rid of this first part of it, right? Like I can come up with a shortcut to say what I mean when I think two documents are similar, right? But you can see the difference in numbers here is pretty big. So the idea is, this is our strategy because we're a big data people, right? So our big data strategy is what we're going to do is we're going to do a comparison, which is an ON squared times an ON compare, right? And we're going to try and make this compare part as cheap as possible. So what we're going to do is we're going to take our document and we're going to try and create a document summary, which is going to be smaller than the document, right? In some way, right? And then we're going to, instead of comparing the document to the document, which will be slow, we're going to get a document summary and we're going to compare it with a document summary, which we will hope will be quick and broadly accurate, right? Like the goal is here, we're going to sacrifice some accuracy for being really, really quick. So if my elements are unique, right? The real numbers, people's profiles, whatever, then ON squared is the best I will ever get for a direct comparison between each individual element, right? Yeah, so that is like the what do you call it? This is sort of like the fundamental rule. But like the idea is that like, oh, well, maybe if I can like hack my way, like what if I like hash both of my documents in some way? And now I just compare the hash signatures and say, oh, well, they might be similar. And now that they might be similar, what I'll do is I'll compare these documents. But these ones with very different hashes are unlikely to be very similar. And comparing a hash is really quick, whereas comparing a whole document is really slow. All right. So today, the whole process we're going to go through is document into shingles, shingles using min hash, and then min hash using local sensitive hashing, right? So these, when I said at the start of the lecture, were like the summary, right? Really, this is just one big process going from too much data to less and less data. Okay, so Jacquard similarity. Let's start with similarity, right? So let us assume that we want a measurement of similarity which follows these rules. Okay, so the rule is, if these two sets are completely different in every way, you can see that there's a yellow triangle, green square, orange circle, gray pentagon, black moon, purple arrow. Nothing in common. I'm going to say they are 0% similar, right? If they're completely the same, I'm going to say 100% similarity. So this is kind of the metric I'm going for. The easiest way of doing this, or at least one of the easy ways of doing it, is basically what you do is you say the Jacquard similarity of sets. And we do something similar in like computer vision. Intersection over union, right? So basically what you do is you go, okay, you see these two sets are the same because both sets contain all the same elements. This set down here are completely different because they have no elements in common. And this set in here has some elements in common. So what we're going to do is we're going to divide the number in common divided by the total number of elements. So does anyone want to hazard a guess for one of these groups? What do we think the Jacquard similarity is going to be? Oh, there it is. Oh, there's my preview. The first one is 2 out of 5, right? Do we get how we did this one, right? So do I get a thumbs up or a clap? I want a thumbs up or a clap. Just pretend people are paying attention, so I don't feel like I'm very lonely anymore. No one is paying attention. 0 out of 6. Oh yeah, cool. Yeah, so 3 out of 3 and 0 out of 6. I like that. Good. All right, so 3 out of 3, 0 out of 6. Well done, right? So we can see here there's 3 in the group and there's 3 in total. Here we can see there are 0 in the middle and 6 in total. And the hardest one is actually the first one. There's 2 in the middle, there's 5 in total. Beautiful. All right, so this one isn't really mentioned online that much, like in the reading. You can like go and Google it. It's not very complicated. The idea is that you've got 2 groups of objects, and if each group can be construed as a vector, right? What is the cosine of the angle between the 2 vectors? And you're like, oh, okay, so if the angle between the 2 vectors is nothing, the cosine will be 1, right? And if it's like pointing the opposite direction, it will be -1, right? So that kind of makes it like, that'll be like the opposite of similar. And then if it's like 90 degrees, the vectors will be like completely orthogonal, and we might say that there's like 0 correlation, right? So I'm like, oh yeah, that makes sense. I like it. Except when I was looking at this, I was like, wait, what? If each object can be construed as a vector, right? What the hell does that mean? Right? Like, as in, I have a group and I'm just going to arbitrarily turn my group into a vector. And the way that you could do this is you do it as a one shot. So basically every element in reality that could ever be, right? You either have it or you don't. And you say it's a 1 or a 0. So you've got this massive multi-dimensional vector, right? And you can imagine that like when both of them have the same value, so both of them are 1, so they both contain a similar element, that vector will be slightly in the same direction as the other vectors, right? There are some like flaws with this because, you know, like basically once you get a large enough number of elements, everything tends to like converge on being orthogonal to itself, like as in any random given data set of points. There's like a little contradiction there in the math. But yeah, this is one way that you can do it. Like, I think Jacquard similarity is probably, from what I've seen, a little bit more legit, or at least like more convincing that it would work. All right, so the next thing that we got is shingling, right? So we know what similar means. Now we need to know, what are we going to compare, right? So what we're going to compare is these sentences, right? Like, okay, right? So this is just an example. It's the easiest one possible, right? So these 2 sentences are like, the quick brown fox jumps over the lazy dog, and the lazy dog was jumped over by the quick brown fox, right? So we can see here that this is basically the same, right? Even though like they contain mostly the same words. There's a was here and there's a ed there, but other than that, there's not much, right? So shingling something, basically, if I do a K shingle, I do a 2 shingle. Basically, I look for every 2-letter combination. So I go THHE, so that's like the first 2 letters and the second 2 letters, and then E space, because space counts, and that should be space Q. I don't know why I have the underscores here, but I don't. That should be space Q, and then QU, right? And then this one here would be TH and HE and E underscore, and then underscore L, and then LA, right? And you can see here already that it's got quite a bit of a matchup with the and like the word the. These shingles would appear in both documents. And then you could imagine that if I kept going here, that quick would still be here because I'd have space Q here and I have space Q there. And then I have QU here and I'd have QU there. And you could imagine, so if I sorted this list of shingles, that these 2 sentences would end up looking like the same list. And if I get rid of any repetitions, I basically just go, oh, okay, so these 2 lists look almost identical. They have lots of similar elements in them, right? So we don't do repeats, right? So this is just a general thing. So like you see how I have an E space and an E space, or I could have an HE and an HE. I don't enter them again. So if I get them twice, I don't enter them again. So you can see here that my shingles are just AZBRCKDO, right? Like as in that's the order if I've sorted them. And then I'd have E space. I don't have 2 E spaces. I just have 1, even though in both sentences I have 2 E spaces, So the question is now, right? How long should a shingle be, right? Because, we have a choice. We have a tunable parameter, right? So with 2 characters, shingles, there are 26 by 26 unique letter patterns, 27 by 27 if we include spaces, 20, 30 by 30 if we include other punctuation, I think, right? But that number's 26 by 26 is 676, which is a reasonable number of unique shingles, but it's not very high, right? If we would have 3-letter shingles, right, that would be 26 by 26 by 26, and that would start looking like a pretty big number. So you can see that, like, basically the idea is that the number of unique shingles that you have is going to increase as you increase K. And the question is that a good thing or a bad thing? And the answer is, well, it depends, right? So we can see here that, like, the shingle WE could correspond to almost any of these words, right? Like, there's more words as well, like you could have or, AWE, you could have weevil, you could have, I don't know, the day of the week, right? But as soon as you go, okay, now I'm only going to have 3-letter shingles, right? You can see here that we've already removed a couple of the options here, right? So like O and U and stuff will disappear. And now we're down to where and wheel and week and ween and wealth and wealthy, right? And then here we got wheel. Well, that's really getting us down to wheel, wealthy, and wealth, right? And there might be some other words. This isn't a comprehensive list. It's just to give you an idea of where we go for a lot of words. The longer the shingle, the less likely the word is. This is kind of cool because the idea is that we want to see if two documents are the same, right? So, as your shingles get longer, you can tell, like, just within language, like, for example, English words have a certain length. If you have a shingle that's like 10 letters long, if your shingles in 2 documents are all very similar, it's pretty much guaranteed that those 2 documents are the same. Whereas if your shingles are only 2 and your document's long enough, you're probably going to have 90% of the shingles in both documents anyway, right? Because you're going to have almost every combination of letters, just because it's very easy to have every combination of letters. And the easiest way of thinking about this is, could you imagine if shingles were just 1, right? Then you'd be like, I'm looking for documents that don't have a Q in them. You know what I mean? These 2 documents are the same because neither has a B, right? Like that's a really bad way of trying to, like, identify 2 documents, right? So the longer it gets, the more likely that they're going to be, that any given shingle, the probability that any given shingle is in any given document it becomes low. Of course, if your characters are really, really long and you have like a 50-character shingle, yeah, there are only unique letter patterns, right? Like, every document is going to be unique. Like, for example, this one by Shakespeare, right? To be or not to be, that is the question, whether it is nobler in, right? Like, really, like, that's pretty obscure. At 50 letters long, our shingles are becoming pretty useless because all of the documents will be unique to each other. Because, like, if I had a typo in any of those letters, it wouldn't recognize the 2 documents to be the same. So, like, I could have a comma here or something, or a lowercase or a typo or something. And even though the documents are broadly the same, the shingles would indicate that they're completely different. Or if I rearranged it, you could imagine that, you could have shingles that are 1,000 long and then they become even more useless, right? So there's a happy medium in there, right? So this is a tunable parameter where we might run a bunch of models, look at a bunch of values, and then choose our shingle size, depending on what the document is about and how likely repetition is in that document. Yeah, so assuming there's no repetitions, there should be 1 shingle in the document per character, right? Minus the shingle length, ignoring all the repetitions, right? So this is the question here. How big is this list of shingles? You think about it, right? Like, okay, let's say I'm doing like 10-letter shingles, right? It kind of implies I'm going to have 1 shingle for almost every character in the document, right? Because it's going to be kind of unusual that I repeat 10 characters again later in the same document, or at least the number of times I do that is going to be quite small, right? So it starts, there's part of me at this point in the thing where I was like, wait, wasn't the goal to try and decrease the size of the data, right? By doing this shingling thing, aren't I kind of increasing the size of the data because I have to store all of these shingles, and there's pretty much 1 shingle per character, and each shingle is actually reasonably big. So it seems like a dumb idea at some level, right? But this is where we get to the next stage. So we've gotten our shingles, right? Shingles are not good enough, right? Like, you can compare 2 documents using shingles, but it's not inefficient. It's not efficient. What it is that all it really does is it allows you to not worry about the order very much, right? So what we've done here is we've basically made an assumption that we're going to take two lists and we're going to kind of sort both of them, and then we can sort of compare them a lot faster. So a good example would be something like merge sort. So, you know, when you're sorting using merge sort, you put them together and you have two sorted lists and you sort of zipper them together, right? So you go like 1, 2, 3, 4, 5, 6, 7, right? So this one's higher, that one's higher, that one's higher, that one's higher. You go from list to list. By doing the shingling, we're doing a similar thing to the way that we would do sorting. We're basically sorting the document in a way that makes sense. We're not just sorting the characters now, which removes all the information. What we're doing is sorting the shingles, which kind of preserves some of the information, but also simplifies the representation so we can deal with it without having to do an ON squared comparison. All right. So here's our one-shot vector that contains all the three character shingles like AAA, AAB, AAC, AAD, etc. Right? So we have 2 to the power of 3 different buckets, right? So in 20,000 buckets to populate, right? So we've got to put all these numbers into buckets. Yeah. Why are we doing this? Because we want to hash, right? But what we're going to do instead, we're going to choose how many elements we have in our array to compare. So what we're going to do is we're going to take our shingle set and then we're going to hash it, right? So we're going to take this set and we're going to hash it into a document, right? So we're going to treat it as a number. We're going to hash it into a document. We're going to make it smaller, right? And then what we'll do is we'll compare the hash of our first document to our second document. This is the theory, right? Like, what are we going to try to do? So we need to come up with an idea of like, how do we keep things very simple? Okay. So we're going to use min hashing to get some signatures, right? So for each document, we want to have a signature per document, right? And what we're going to discover is that actually we want to have a couple of signatures per document. One signature is not good enough just because of randomness, I guess, but we want to have a couple of signatures. If we get a couple of signatures per document, it's very unlikely that we're going to have 2 documents whose signatures are all the same, right? So each set of shingles is large. It's proportional to the size of the document. Okay, yeah, that's fine, right? So we've got lots and lots of shingles. There may be millions of documents. We're still not good. We're going to, how are we going to store all this stuff? All right, so we're going to do it via min hashing. Okay, so here is the method, right? Here is our documents, S1. And we're going to say, like, just for the sake of argument, it's really, really tiny documents, right? Basically, we're going to have 5 shingles per document. Yeah. And so what we're going to do is we're going to say, okay, for document 1, right? We've got 2 shingles. It's got an A and it's got shingle D. Document 2 has shingle C. Document 3 has shingle B, D, and E. And document 4 has A, C, and D. So if we were to do a direct comparison now, right, and we want to see how similar they are, we would say that S1 and S2 are not similar at all. They have nothing in common. S1 and S3 are very marginally similar. So they have a total of 1, 2, 3, 4 distinct elements. But according to our Jacquard similarity, it's like 1 in 4, right? S1 and S4. Oh, that's looking pretty good. That's like 2 similar out of 3. So 2/3. That's pretty good. 2 and 4 is 1 out of 3. And then 3 and 4 is what, 1 out of 5, right? And then is that all of them? Those are all comparisons. So that's what we've got, right? So those are the kinds of numbers that we're looking for. We're looking for a way to like really simplify how we calculate that. So what we're going to do is we're going to permute all the rows randomly. So if you look carefully here, instead of having A, B, C, D, and E, I now have B, E, A, D, and C, and I've rearranged all of these numbers to correspond, right? And then I'm just going to select the first one in each column. And that's it. I'm going to say you're A, right? And so I'm going to say the hash signature of S1 is just A, and the hash signature of 2 is just C, and then B, and then A, right? And so what I can do then is I'm going to be like, hey, look, 1 and 4, they're the same. Woo, that was easy. But are they the same? Like, I don't think they are. They're mostly the same. But it did get to the core point of it, right? Like, as in 1 and 4 are basically quite similar, right? So we're like, oh yeah, this is not a bad way of doing things. Okay, so we might come to the conclusion S1 and S4 are the same. But what's the probability that we were right? Now, this is kind of interesting. It's the Jacquard similarity. Now, why is this? Why is this? Okay, let's think about this for a second, right? If I just randomly sort it, what is the probability that I get one of the rows where they match? Well, it's the probability I get a row that they match just happens to be, right, 2, right? There's two rows where they match, yeah? And there's 1 row where they don't. So there's like a 1 in 3 chance that I would get the row where they don't match, and then I would get like a 1 for one and something else for the other. But there's a 2 in 3 chance that I would get the row that does match if I'm just looking for the first one, right? So there's a 2/3 chance, which just happens to be the Jacquard similarity, right? Like, so we can think about this. I think, did I have the proof in here? I don't think I had the proof in here, but that's like the logic of it's pretty sound, right? Like maybe I'll just do it here. Do I have a video? I don't know if I do. Let's do that. Paint. Okay, so like, do I want paint? I don't think I want paint. I think I want PowerPoint. PowerPoint. So imagine I've got two sets, right? Like insert, what's it, insert table, right? And I want to compare if they're the same, right? So what I can do, home, and I'll just start here. I'll be 1, 1, 0, 0, 1, 1. And then this one, I'll be like 1, 0, 1, 0, 1, 0, right? So if I just randomly shuffle them, right? These are the rows where they are the same, right? Where they are the same. Now, do I have any 0, 0 rows? Yes. Okay, so those are the rows where they're the same. I don't need to worry about the rows where they are both 0 because neither of them are going to get picked as the first one if they're both 0, right? So the only columns I need to worry about are these yellow ones, right? So basically what I'm saying is, what is the probability I pick an orange rather than a yellow, right? And the probability is, well, I've got 2 oranges I could pick and 3 yellows I could pick. So the chances of me picking an orange is 2 out of 5, right? But definitionally, the Jacquard similarity is where these are both 1 and these are both 1, and divided by where they are both 1 plus where you have a 1 and a 0 or a 0 and a 1, right? So it just magically turns out to be the Jacquard similarity, right? So this is going to be important going forward. So it's an important thing to like keep in your head that the probability that if we do a min hash and just magically rearrange the row and just say the first thing that I find, that's going to be what the hash is going to be, there is a Jacquard similarity probability that I am right. Yeah. So my Jacquard similarity is 80%. There's an 80% chance that if they are the same, that is right. Yeah. There's a 20% chance that if they are the same, that was actually wrong. But, you know, I'm going to use that math going forward. Is it good enough? No. Right? So there's a couple of problems with this, right? Firstly, permuting the matrix could be hard, right? Like as in, I just said here where I was just, I'll just permute the matrix. Maybe the matrix is huge, and so that would be hard. We have a way around that, right? The other problem is obviously that we are only P-Jacquard similarity, right? Oh, sorry, permuting the matrix is hard and impossible. We could use a hash function to simulate the permutation, right? Like, this is where, you know, computer scientists were involved. They're like, oh, but then I might have to sort it. But what if I just made a hash and then I picked the row according to the hash? Then I wouldn't have to sort it. So I'll create a whole bunch of hashes and then use them as my randomization. So we're using hashes to get hashes. Like by the end of this lecture, you just be like, wait, how many hashes are involved in this? So we're only P-Jacquard similarity right. Okay, so that's not very good. One of the solutions we could use is we can use multiple permutation hash functions. So basically the idea here is that we do it once and then we do it again and then we do it again and then we do it again, right? And now we'll have like a couple of guesses. Yeah. So like I basically shuffled it, right? And oh, did I get rid of my old one? I did get rid of my old one. We shuffle it, right? And say I have like a 50% chance of getting it right. Well, now if I shuffle it and do it again and do it like 10 times, I'll probably have 5 right ones and 5 wrong ones, right? And so that'll tell me, I'll be like, oh, okay, yeah, maybe they're not that similar. Whereas if I had one that was 90% the same and 9 times out of 10, they are the same, I'll be like, oh yeah, maybe they are similar, right? Or 1 time out of 10, right? Whereas if you only did 1 and you got that 1 time out of 10 where you said that they're similar, but actually only 1 time out of 10 they are, it just happens to be you picked the 1 out of 10, you get a completely wrong answer. But if you did it 10 times, you're very unlikely to get a wrong answer. You're very likely to get it wrong 9 times out of 10. Or at least wrong quite a, the probability of getting it right 10 times out of 10 when the chance is 1 in 10 is like 1 in 10 billion. So that's not going to happen. So here's a good question. How many hash functions do we need, right? Like, so that's another one. So we've already got k-shingles. Now we're doing min hashing. How many hash functions? How do we implement it? Yeah. All right. So here's an example, right? So what we're going to do is going to have two hash functions. We have our two hash functions, one h1, which is x plus 1 mod 5, and the other one's 3x plus 1 mod 5. So you can see here that like basically 0 goes to 1, 2, 3, 4, 0 instead of 0, 1, 2, 3, 4. So we've just moved it on 1, so x plus 1. And the other one is x times 3, so you can be like 1, where is it? 0, move on to 1, move on to 3, move on to 3, move on to 4, right? So here's our process, right? What we're going to do is for each row, we're going to find sets with a 1. Yeah, for each row, we're going to find sets with a 1. So like if we did row 0, S1 and S4 have a 1. We're going to set their value to the minimum of their current value and the new row value H1 or H2, right? So what? Let's go. Let's see it all done, right? Okay, so we've got this H1, right? And H2, according to hypothesis 1, we've got S1, S2, S3, and S4, right? We've got H2, infinity, infinity, infinity. We started infinity because we're trying to minimize our hash, right? So what we do here, right? Oh, wait, I'll just make sure I get this. My animations are right. Yeah, cool. So we're going to start here. We're going to grab these ones here. And they say, oh, these are the ones we're considering because they hash to 1, right? Yeah. And the minimum row, the row, right, is 1, right? So we're going to say that the top row here is 1. So this one's a bit ambiguous because it's all 1s, right? But basically, we're going to take this 1 and put it here in the blue, and we're going to put it here in this one here, and we're going to follow the red to go to here, and we're going to follow the red to go to here. All right. So far, so good. We're following the process. Still have no idea what's going on, right? Now what we're going to do is going to go to the next one. This one is a 1, right? So we're only going to consider row 3. And now what we're going to do is going to go, hey, it's a 2, and this one is a 4. Okay, yeah, all right. So that's more clear. I can see what's going on here. But what does this 2 and this 4 represent? Well, what this 2 and this 4 represent is basically it's a row, right? It's the row where the thing is equal to 1, right? So we're just going through trying to find what the first element is, right? Like the first one. So we're applying all these hashes to randomly sort it, but we don't actually want to sort it, right? And we're just trying to find the first one. So we're just trying to calculate, like imagine we're trying to do a shortcut. We've got, 1,000 documents. We got 5 million rows. We're going to randomly shuffle the rows, and we want to know which row for document 10 was the first one without going through it sort of laboriously and then like just going through it randomly like this. What we're going to do instead is we're going to go through, and whenever it is a 1, we're going to look at what the hash would be, and then we're just going to set it to the hash. And if the hash is smaller than the hash that we've got already, that just means we set it to the smaller number, right? So here what we've done is we've set it from infinity to 2 and 4 because we started with infinity, but it's not particularly helpful. So let's move down one row. And this is where we get to the like, oh, an interesting part, right? So we should be looking at number 2 and number 4. Right? Now, number 2 is fine. We just fill it in with the numbers. We put in the 3 and in the 2, right? But why do we not update number 4? Well, we don't update number 4 because hash 3 is bigger than 1. And hash 1, which is 3, is bigger than 1. And hash 2, which is 2, is bigger than 1. So we don't make these smaller, right? So again, we're still not quite at the core of this algorithm yet. What we're going to look at is the next row. And this is the one that actually matters. You can see here that we're going to try and update S1, S3, and S4, right? And we can see here that there is a 0, right? So what this is saying is that basically in row 0, according to this hash, there is a 1 for each of these, right? And so the row at which I should pick this value's hash is this row. Right? So is this 0? Yeah. So basically these ones are all in row 0 because according to one of my random hashes, right, my hash 2, all of these values would have been in row 0 at the top. When I randomly shuffled it, all of these rows would have been in row 0 at the top. So they would have been the top one, which would be the one that I pick, right? So they would be the top number, right? So basically now I set these all to 0, right? So this was a 1, it goes to 0. That was a 2, it goes to 0. That's a 1, it goes to 0. Now, none of the top ones change, right? Because this is 4, and 4 is bigger than literally everything. But we're not quite done yet. We still got one row left. So let's predict what's going to happen in this last row before we click onto the next screen. The only one that could get potentially updated is row 3, right? Now, interestingly, row 3 is 2, 0. I'm not going to update the 0 to a 3, but I certainly will update the 2 to a 0, right? So this basically means under this hashing, right, under hash 1, row 4 is actually row 0. And if we go back to our hashes, that makes a lot of sense, right? Because where's our hash function, right? Row 4 is 0, right? So that would be the first row, right? So we would be like, oh, actually, this would be the first row. If this was the first row, the first thing for S3 would be the first row, yeah? Under hash 2, which is 3x plus 1, what would be the first row? What hashes to 0? 3 times 2, 3 times 3. Row 3. 3 times 3 plus 1 is 0, hash 4. So if I go to row 3, I can see that hash of 2 is also 0. So for hash 1, row 4 is 0. And for hash 2, row 3 is 0. So when I shuffle them, S3, when it is hash 2, would be at the top. So it would be a 0. So this row would be at the top, right? And when it's hash 1, this row would be at the top. And so S3 would still be 0. The first row, which has a 1, would be the 0th row, right? And we can see that here, they're both 0s. Okay, cool. Do we get min hashing, right? Like this is just a fancy sort of like in place, non-sorty way using hashes to basically keep track of where the top 1 is. That's all we're trying to work out. It's just a fancy way of doing that. So we're just like, I want to randomly shuffle it and work out where the first 1 is for each book in our or each document. Okay. So now I have my similarity estimation, right? And now I can calculate it out and I'd be like, hey, the number of rows that are the same. How many rows are the same? Okay, well, how many rows are the same? S1 versus S4, they're all the same. S1 versus S2, none of them are the same. S1 versus S3, one of them is the same. H2 is the same for S1 and S3, right? So you can see 0 the same, 1 the same. Oh, maybe I'll do annotate. So, none are the same. So we get none. 1 is the same, which is this one. That's the same. So we get 1. And then I'll get back to my blue. 1, 0. Oh, look, 1, 0. They're all the same. All right, so that's pretty cool. And the question is, was it worthwhile? Is this at all accurate? If we work out the original Jacquard similarity from the matrix, we can see that it's 0 out of 3. Oh, so 0 out of 2, 0 out of 3 is not too bad. A half compared to a quarter is not too bad. 2/3 compared to 2 on 2 is not too bad. 0 out of 4 to 0 out of 2 is not too bad. 0 out of 2 compared to 1 out of 3, it's not too bad. 1 out of 2 compared to 1 out of 5, that's probably not that great. But the point here is that we're with only 2 hashes, we're already getting close to the truth, right? And the hash is not a particularly complicated operation to do because we're just creating a fake hash to randomly scramble it. And then we're just going through document compared to shingles. So it's not too bad, which is kind of close to what we'd have to do anyway. All right. So locality sensitive hashing. All right. Keeping things together. Okay. This is the complicated part, right? So far we're just we're going to make some shingles. We're going to just randomly sort our shingle lists a bunch of times, right? And then we're going to pick the first shingle that appears in the list, and we're going to use that to compare the 2 documents. We'll do it, I don't know, 10 times or something like that, right? And then if those 2 lists are the same, then we think the documents are the same. If they're different, we think the documents are different. Okay. Here we go. Here's a logic. Similar items are more likely to be hashed into the same bucket than dissimilar items. That seems reasonable, right? If the 2 documents are very similar, there's a good chance they'll end up in the same bucket. So if they're in the same bucket, I'm yeah, they're probably similar. So the goal here is what we're going to do is we're going to consider pairs which we find in the same bucket. So I've got 2 documents that I hashed into the same bucket. And we're going to do this a bunch of times. So some proportion of the hashes are the same. So, like as in I hashed document 1 and hashed document 2 by hash 1, and they went into one bucket. It was the same bucket. And I hashed document 1 and document 2 by hash 2, and they both went into the same bucket. So I'm like, oh, wow. And then I hashed document 1 and document 2 by the third hash, and they ended up in the same bucket. I'm like, oh my God, these documents must be similar. That's kind of idea, right? The problem with this is, of course, is that two items can hash to the same bucket erroneously. Document 1, document 2 have nothing to do with each other. I did a hash. Hash has a collision-y thing. I have two documents that hash to the same bucket. I'm like, oh, it told me they were the same, but they weren't really, right? Now, the likelihood that that happens repeatedly is pretty low. So the idea is the more times I do a hash, the less likely it is to hash into the same bucket. So that's kind of good. Then I have the probability that, two similar items hash to different buckets, right? So like if I have two similar items, they're very, very similar. And every single one of my hashes, for some reason, just managed to get them where they hashed into the different buckets. Now, an example, I don't know, like that seems like a far-fetched example. So I might just see if I can confect a really simple example of how that would be the case. But you can imagine a case where like you've got a bunch of things like this, and your buckets are like 1, 0, 0, 1, 1, 1, right? And you're like, I'm going to hash this a bunch of times. And for some reason, every time I hash, it basically picks this column, right? So it goes, like this is the crappy column, or it picks this column, right? And you can imagine that even if these documents were like super similar, there is a small chance, an outside chance, that all of the hashes, right, just happen to always sort this to the top and always sort that to the top, or one of these two. And now, even though these two documents are the same, like virtually the same, just because of random chance, and because my hashes kind of weren't that random, they look different even though they are the same. So that is a false negative. So those are the two possibilities. Okay, so now to do some math, right? What we're going to do is we're going to take the hash signature of a document, right? And we're going to band it into a bunch of rows, right? So we're going to have a hash signature of a document, right? So we're going to hash it like a bajillion times, right? And we're going to, like, let's say so imagine that you've hashed this document like 100 times. Now this is beginning to sound insanely expensive, but it's actually still cheaper than trying to like compare it to every other document. So like, even though it sounds really expensive, it's not. But let's say I've hashed it 100 times. What I'm going to do is I'm going to take the first 10 hashes and the second 10 hashes and the third 10 hashes and compare them to other documents. So I'm going to go, are the first 10 hashes of this the same as the first 10 hashes of that? Are the second 10 hashes the same as the second 10 hashes of that? Are the third 10 hashes the same as the third 10 hashes of that? And now I'm going to use some logic and power of math to try and make it so I can really simplify this process. So not only did I hash originally, and not only did I hash to sort so I could min hash, so I hashed to hash, now I am going to hash again, right? I'm going to put them into bands, right? With R rows each, right? And so again, these are now R tunable parameters. So we start with K shingles, and then we've got number of hashes in total. So how many rows there are in total. And then once I've worked out that number of rows in total, I'm going to split them into bands. And then each band has a number of rows. Okay. Well, each band hash, oh my God, it's portion of a column, right? Okay. Right. So for each band hash, it's portion of a column, a segment of the signature to a hash table with K buckets, right? So this column, this hash signature might be really long, and it might still be too long. And you're like, oh God, really? It might still be too long. Are you serious? Okay, so what I'm going to do is I'm going to simplify it. I'm going to hash it down to a smaller subset. So maybe that signature is like 15,000 hashes long, right? Because apparently I can do 15,000 hashes. And I'm like, I don't want to compare 15,000 hashes. What I'm going to do is I'm going to hash it down to like 200 hashes from 15,000 hashes. You're like, oh God, all right, I'm going to hash from hashes down to 200 hashes. Okay, let's assume that I do that. I hashed it down again. What is the likelihood that I end up in the same bucket? Oh, if they're the same, 100%. And if they're similar, some other percent, which is related to my Jacquard similarity, right? Like probability of hashing a signature, which is already a hash, which I made using hashes down to a, oh God, down to a band, right? So like, I want you to imagine all of these numbers, let's just imagine that we've got a really confected document, and each of these are the numbers from like 1 to 1,000,000. Yeah. So each hash, just coincidentally for this document, hashed down to 1 to 1,000,000 buckets, right? For some reason. Or maybe not even that. Like maybe it's all of them are, it's just like 1 to 1,000 repeated 1,000 times. So it's like 1 to 1,000 repeated 1,000 times. Now I want to break it down into bands of 10 bands. So each one is going to be like 1 to 1,000, 100 times, right? I don't want to do 100,000. So I'm going to hash my 100,000 things into a new hash, and I'm going to hash down to like 100 things. Okay, now I've got 100 different things. If those two hashes were originally identical, what's the probability that they get the same hash? It's 100%, because of course they're going to get the same number. If they're 80% similar, what is the chance that they're going to get hashed to the same thing? 80%, because we know this Jack-O-Lide similarity. Right. Okay, so now I know that. Okay, candidate pairs. So we're going to basically go, the ones that I care about are the ones that are going to get hashed to this mini bucket inside a mini bucket. All right. So I've got this document, and I'm going to take this band and I'm going to hash it down to a bucket. This one is different from that document because it hashes to a different bucket. This one is the same because they could be the same document. They could be very similar because they both hash to the same bucket. So now I'm like, okay, they both hash to the same bucket. They're probably similar. They hashed via a min hash to the same bucket. They might be the same thing. There's a pretty good chance. Okay. Right. So I've got B bands and R rows and Jack-O-Lide similarity of S. The min hash probability of two documents agreeing is S. Okay, so that's fine. So I say there's a 50%, 80% chance that they're the same. The probability that all the rows agree. Now the rows, there's I don't know, lots and lots of rows. What's the probability that they're all going to agree? The probability that they all agree is basically the Jack-O-Lide similarity to the power of R, right? So like if they are 90% the same, but there's 10 rows, there's a 90% chance that all the rows, like the row matches, each row matches, 90% chance, and I have 10 rows, the probability that they all match is 0.9 to the power of 10, right? Which is actually not a very good number. Now, that's fine. Now I have the probability that they disagree in at least one row. So this is the probability that they are not the same. It's just going to be 1 minus the probability that they are the same, that they are all the same, probability that they are not all the same. At least one of them is different. This is going to be the probability that at least one of them is different. At least one of them is different in every single band, right? So this probability raised to the power of B, right? And this is going to be the probability that signatures agree in all rows of at least one band. So this is the probability that in one of these bands, they match. At least one, right? In at least one of the bands. So if I pick this band and I match it with this document, what's the probability? It's this. Oh, sorry, it's not this. It's like just one of them, right? But what is the probability that in at least one of these rows, these two documents match? Is this expression. Okay, so in pictures, right? If we can think of it this way, right? Imagine that we've got two rows, right? The probability, in this case, the R would be 2, right? The probability that they match is going to be, 1 on like S, right? So S squared on 1 squared will be the probability that they match, right? So S squared essentially, because S squared is less than, because 1 squared is 1, that's why S squared, right? So that's the probability that one document matches in 2 rows of one band, right? Now I've got 4 bands, yeah? If I add all the reds together, right? It's the probability that this one was a red, and this one was a red, and this one was a red, and this one was a red is this expression, 1 minus S to the power of R to the power of B, right? That's pretty unlikely that they're all red. This is the probability that at least one of them was green. That is to say that it matched in all of the rows. Okay. So hopefully this is a high number, right? Like as in like what we're really hoping for is if the documents are quite similar, that this expression is big, right? And then if the documents are very dissimilar, that the documents are, like the number is quite small. So let's do some numbers. Let's assume that 80% similarity. So we're going to say the documents are 80% similar, right? We have 20 bands and 5 rows per band. Probability that in any given row, they're identical is 32%, right? The probability that we have no similar bands, right, is going to be 1 minus S to the power of R, to the power of B, which is 3.5 times e to the minus 4. So the probability that if these two documents are 80% similar, that in none of these bands they match, it's like less than 0.1%, right? Very, very small, right? So let's assume 80% similarity, 20 bands, 5 rows per band. Yeah, okay, that's what we had before. This is probability of false negatives, right? False negatives very, very, very low. Okay, let's assume that we have 40% similarity, right? So the documents are 40%. We don't really want to say these two documents are the same because they're not actually that similar. We have 20 bands, 5 rows per band. Probability that they're identical is this number, 0.0102. The probability that they have no similar bands is this number, right? 1 minus this to the power of 20. And we work out that the probability of a true negative here is about 80%, and we got about 20% false positive. So that's not great, right? 20% false positive, but we've got almost no false negatives, right? So if we were to search through this thing, we can cut down the data by an order of magnitude using this method, right? Because basically, if we only consider where we have these collisions, where we've got two that were in the same bucket, and we think, oh, that's a good candidate, the chance of it actually being a false positive is only about 20%. And the chances that we'll miss one is almost 0. If we assume 20% similarity, you can see here that the number of false positives goes like way down, right? 0.64% false positives, right? That's very low false positive rate. So that's just the same calculations as on the right. So what are we actually trying to do here? Like, so this is just to give you an idea of what the point is, right? Imagine we have two sets, right? And we want to calculate the similarity of the two sets, and we want to work out the probability of sharing a bucket. Ideally, what we really want is we want to have a situation where we say at some point in time, if they are similar enough, they will always be in a bucket together, and below some amount, they're never in a bucket together. So we can easily detect if there are two in the same bucket. That's an easy calculation to do. And what we want to say is that if there are, then they must be at least this similar. And if they are not, then they are not similar. They are at least this similar or less, right? So we can say, oh, we're looking for all the documents that are 80% the same, right? And then we'll be like, oh, well, if they're in the same bucket, there's an 80% chance, like there's a 100% chance that there's an 80% similarity, right? And then this is ideal, we're not going to get this. And if they're not in the same bucket, it means that their similarity is less than 80%. Unfortunately, Jacquard similarity, right? If we just did this normally, just gives us a straight line, like the probability that the similarity and the probability that they're in the same bucket is, like exactly the same, right? Like we discussed that earlier, right? And what we can see here is that, like, if we think of it this way, right? If we have some threshold T, the false positives are going to be when, what do you call it? Sorry, let me just, sorry, I'm a bit tired. The false positives are going to be, right, when we're below the threshold, right, below the threshold of the similarity of the two sets. So they're not actually that similar, but we're like below the threshold for the probability here, right? So we go, oh, these are going to be false positives, right? And then likewise here, these are going to be the situations where we got the wrong number. The likelihood of being in the same bucket was what do you call it? The likelihood of being in the same bucket was wrong. So basically, even though we know the sets are very, very similar, we're going to reject them and say they weren't similar enough, right? So on the right, is this one on the right? Yeah. So what I've done here on the right is I've basically taken this formula here, where is it? This formula here, and then plugged in some numbers to show you sort of what we're trying to achieve in math, right? So like now, this is the standard case where I have one band and one row, right? And that's basically just me pretending to be Jacquard similarity, right? Now what I do is if I go, say if I have 5 rows, right? What happens is the similarity matrix ends up looking like this. So what you can see is the probability that one or more similar bands is like this, right? And that's the similarity. So if I had a probability, like if I got 2 similar bands, I could sort of say, oh, like 70% of the time, that means that they would be 95% the same, right? Which is not good enough, right? But when I start increasing the number of bands, what I can do is I can shift this across and produce this sort of sigmoid curve, right? And I think that's the last one I've got. But basically what this is saying now is that if they are 80% similar, there is an almost 100% chance that I'll end up with both of them in one bucket. right? So I just need to check, are you both in the same bucket? Like, I get all of my documents and I go, in any of the bands, did you match with the other document in any of its bands, right? And because I've hashed these things, these comparisons end up being reasonably cheap, right? And if so, if you have at least one, right, I can be pretty much like 80% confident that you're probably going to be a good one, right? Like as in like that you are at least 80% similar, right? If what do you call it? If you're similar in all of the probability, if you're similar in all of your bands, you're probably 80% the same, right? So simplifying the calculation, it turns out that this nasty calculation, wherever it is, this nasty calculation can be approximated by a simpler calculation, which is this, right? And so basically what you can do is you can calculate this, and this gives you like the threshold, like basically the inflection point of this thing, right? So you can see here that the 1 on B to the power of 1 on R is the red line, right? So what we're doing here is we're basically just saying, oh, I can adjust my B and my R to basically work out where I want my threshold to be. So if I'm looking for things that are like 70% similar, what I could do is I just adjust B and R until this formula ends up being as about 0.7, right? And then I will have a curve that looks broadly like this. And the higher B is and the higher R is, the steeper and sharper it will be. And the closer it will get me to the map that I want. So if we summarize the whole thing, basically the idea is we're making our shingles. We need to choose a good K, right? So that's the main thing with the shingles. How many letters in a row? We sort the document into shingle pairs by shingles. We pick and choose a number of min hash signatures. We need to choose a good n. So we have a bunch of n hash signatures. We use these hashing functions to like sort them, to pick the first response in each document. So whatever the first shingle was, we can use those comparisons and go, under hash 2, was your first shingle AB? Mine was AB. We might be the same document. Likewise, what we do is we go, then we choose a similarity T. How close do we want them to be? Like 70%. We can tune a B and R according to this formula here, right? And then we group all of these things into bands and rows, and then we compare the bands and go, are your bands 100% the same? If they are, do they hash to the same bucket? Now I can just check the buckets. Did your hash? I'm just going to hash all of your bands. Document 1's band 1, document 2's band 1. They hash to the same bucket. I'm going to bother to check whether document 1 and document 2 are the same. I think they're similar enough. I think they're similar, right? Did all of them miss? If all of them missed, they're almost certainly the wrong document, right? Like there's a 900% chance that it's the wrong document. Cool. And that's the end of that. Now sorry, I don't have time for questions today because I've run over a little bit. If you have any questions, feel free to like email me for today's lecture, because I literally have to go. I've got to go right now. It's 3:10. But is there any like super quick question? Like super quick. All right. Doesn't look like there's any question. I'm going to be on my way. Thanks for coming.